Dear students, we'll see the numerical problems related to parallel connected resistors and the current divider rule. In the previous class, we have discussed about how to find the equivalent resistance of parallel connected resistors and when to apply current divider rule. We'll try to use those concepts of parallel connection and current divider rule for solving numerical problems so that by the end of this class, you should be able to determine what are the branch currents and voltages and also the equivalent resistance of parallel connected system. So we know that for parallel connected resistors R1, R2, R3 like this, we can find out R equivalent and R equivalent is given by 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R2. So here voltage by current is resistance and the current divided by voltage is 1 by resistance. So this is current by voltage. So this is 1 by R equivalent. Okay. Yeah. So consider this problem. Find the effective resistance means equivalent resistance you have to find between the points A and B here. These are the points, nodes A and B. So what we have to do is A and B should be there as it is. The other nodes like C, D, E, F can go when you combine the resistors. See the possibility of combining these resistors and finally it should result into a single resistor between A and B. So at a first sight, this circuit seems to be complex, but observing carefully, it is possible to combine the outer resistors and approach to a single resistance. See here, is 3 and 3 are in series. 3 plus 3 will become 6 ohms. That will come in parallel with 6 ohms. So 6 and 6 in parallel, that again becomes 3 ohms. If two resistors of same value are connected in parallel, then the equivalent single resistance will be half of that one. 6 ohms and 6 ohms are connected in parallel, then its equivalent resistance will be 3 ohms. So like that you have to step by step solve. See here, RAD, between RAD, if you see, these 3 and 3 are in series, that becomes 6. That will be in parallel with 6 ohms. So that is what is given. 3 plus 3 in parallel with, this symbol is parallel, in parallel with 6 ohms. So 3 plus 3 is 6 in parallel with 6. That comes to 3 ohms again. Now this all will form into a single resistance of 3 ohms. And that 3 ohms will be in series with this 3 ohms. So that becomes 6. So RAD is 3 ohms. That is in series with this 3 ohms. So you will get 6. That is in parallel with again 6 ohms. So what happens? 3 plus 3, 6. In parallel with this one, again you will get what? 3 ohms. This again reduces to 3 ohms. So this 3 and this 3 are in series. That becomes 6 ohms. That will be in parallel with this 6 ohms. So 6 and 6 in parallel. Again, this also will go and come to 3 ohms. That is this one. RAF, between IA and F. It is totally 3 ohms. These many resistors are there, but finally it is one single resistance equivalent 3 ohms. And that 3 and this 3 are in parallel. So that becomes 6 ohms. So finally you'll get what? 3 ohms between A and B and 6 ohms is there. Okay. So this combined is 3 plus this 3, 6 ohms. 6 plus 6 and 3 are in parallel. So that equivalent resistance between A and B, RAB or R equivalent is equal to, as these are connected in parallel, this will become 6 into 3 divided by 6 plus 3. So what is R equivalent formula? R1 into R2 divided by R1 plus R2. So that is nothing but 18 divided by 9 equal to 2 ohms. So similarly, current divider rule. We know that applying KCL here, I will be equal to I1 plus I2. And from that, we'll writing the voltage equations and current equations. You can arrive at this one. The branch current I1 is total current into resistance of the other branch divided by sum of the resistors connected in parallel. Same thing for I2. So using current division rule, find the current flowing through each branch of the given circuit. So here this one is a current source. It is giving a current 10 amperes. So this total current IT, okay, this total current IT will be equal to 10 amperes. And this divides into what? I1 and I2. So as per current divider rule, what will be I1? I1 will be equal to total current into resistance in the other branch, 15 ohms divided by sum of the resistors connected in parallel, that is 10 plus 15, equal to 150 divided by 25. So that comes to 6 amperes. 6 amperes current. Similarly, calculate I2. Try out this. Here it is given. I2 is 4 amperes. So dear students, we have seen a problem how to calculate the equivalent resistance for parallel connected resistors and how to calculate the currents for current divider rule. So consider this circuit now. This complex circuit is there, but you can analyze, gradually come to AB. Find the equivalent resistance, let us say here. Okay. Find the equivalent resistance RAB. How will you find it? Okay. Step by step, we solve it. 500 ohm resistors are connected in parallel. So there are 5 resistors connected in parallel. Okay. They are connected in parallel. If one resistor is removed, if I remove this one of the resistor, what will be the total resistance? 100 ohms is there. So that means how many resistors will be there? 4 resistors will be there. So this is 100. This is 100. And this is 100. So I can do like this now. This 100 and this 100 are in parallel. When I combine, they will become 50 ohms. This 100 are in parallel. When I combine, they will become 50 ohms. 50 and 50 in parallel. So finally, you will get to 25 ohms for 4 resistors. The total distance is 25 ohms. Yes, 25 ohms. Yeah. So having discussed on this, now we should be able to solve the problems to determine the equivalent resistance and branch current and voltages for parallel combination of resistors and applying current divider rule. So students, you can refer this textbook K. Umarov, Basic Electrical Engineering, and the topic 1.3.3 in chapter 1. Okay, thank you, students.